Welcome to my first YouTube video. I call this effort Irrelevant Density because I would like to answer claims in the flat earth community that gravity doesn't exist and that relative density is the reason things fall down or plant themselves on the living room floor. The theory, which we'll show is not supported by observation, is that Newton's apple fell from the tree because it was more dense than the air surrounding it. That's not how the world works. Relative density is an incomplete explanation of buoyancy, and it's a completely inappropriate substitute for gravity. Gravity is a force that acts on mass without regard to density. No matter how loosely or tightly you package a bunch of stuff, on Earth it will experience a downward force of 9.8 newtons per kilogram of its mass. So will everything around it. You measure the force of gravity every time you step on the bathroom scale. We'll see how that downward force of gravity can be redirected up. There's really no mystery to that once you see it in action. Gravity is also a funny thing in that it provides a downward acceleration. There is no fixed force of gravity. Go on a diet, not a bad idea for many of us, and you start producing less force on those scales every morning. Pig out on pizza, you're gravity's best friend, but gravity didn't change. You did. Gravity is a constant acceleration on Earth of 9.8 meters per second squared. How much force comes from that is set by how much mass it's acting on. Density is an interesting yardstick. It has a place, but density relationships do not create forces. Those who say relative density causes what most folks call gravity are stopping short of a complete explanation. In fact, the upward buoyant force experienced by an object submerged in fluid is unrelated to the density of the object or its weight. Hear me out if that doesn't sound right. Evidence is forthcoming, but we don't need to perform lengthy scientific experiments. No math is required or presented, but you should realize you can't escape math. If you see two kids balanced on a seesaw at the park, you're not just looking at a couple of happy kids. You're looking at an equal sign. That's math writ on the physical world, and sometimes that's all it takes to see the general nature of things. Let's take a look at three different objects, ballasted so they have individual and distinct densities. All three have the same volume within the limits of manufacturing quality control. All three weigh different amounts. To fit common usage, I'm going to cite weight and force in the units indicated on my scale. It reads in grams, which are properly units of mass, not weight or force. Divide indicated grams by 98 to convert to newtons if you would like, but I'm just going to use the numbers on the scale for clarity's sake. The least dense of our three test objects is empty of anything save air. It indicates 17 grams. Our middle density object is about half full of BBs and indicates 269 grams on the scale. The most dense of our three test objects is chock full of BBs and tips the scale at 507 grams. We'll measure the buoyant force each of these objects experiences with a glass of water. As you can see, it weighs 667 grams, but that doesn't matter. In fact, let's zero the scale to keep things simple. We'll start with our least dense object. It weighed 17 grams. Note that when I set it down in the water, the glass shows a weight increase of 18 grams. This is a cheap scale, and at one point the scale reads the expected 17 grams. To the best of Walmart accuracy, setting an object that will float on top of the water adds its weight to the scale reading. Watch what happens when the object is submerged by pushing it underwater. The weight goes up by 123 or 124 grams, and that's pretty easily explained. When I pushed the object underwater against its tendency to float, I was pushing down against the scale as surely as if I'd pushed directly on it, and the weight didn't just come out of nowhere. When I was standing beside the scale, my full weight was supported by the floor. As I leaned a little on the object I was submerging, I transferred 124 grams from my weight to the object, through the water, to the scale, against the cooktop it's sitting on, and eventually back to the floor. The floor is still supporting my weight, the stove, the scale, the water, and everything you see here. When I pushed down on the floating object, I redistributed weight. I didn't create any. Note that as the object is submerged and retrieved, the level of water goes up and down. More on that in just a moment. Now let's submerge the middle density object. It has the same volume, but it weighs 269 grams and it has a tendency to sink. When I allow it to settle below the surface of the water, the weight goes up by the same 124 grams as caused by the less dense object. This time, I'm holding the object up, but once it's in the water, I'm not having to lift as much. The first object took 124 grams of push, counting its own weight. This one requires 124 grams less lift to hold it in a position where it's submerged, but not touching the sides or bottom of the glass. In both cases, the measured weight of the glass increases by 124 grams. Finally, let's dunk the most dense object, the one full of BBs and weighing 507 grams. The readings vary a little, but it settles at 124 grams. Within the precision of this cheap scale, that's the same added weight as the other two objects. Now let's set the object on the bottom. The least dense object, when left to fend for itself, added its 17-gram weight to the weight of the glass. This shows an added weight of 505 grams, not quite the full 507 we originally measured. But notice when I take the object out of the water, the scale doesn't return to zero. It shows minus 2 grams. I attribute this to water lost by submerging and retrieving the objects and to drift in the scale. Let's re-zero the scale and see what we get. $125 grams, 507 grams. It's a cheap scale, but pretty darn close. We've already seen that all three objects lend the same additional weight to the water when they are held in place within the volume of the water. Let's take it a step further. Keep in mind how we see the water level rise and fall as we submerge and retrieve the objects, always seeing about 124 grams of added weight. I'm pushing against the buoyant force on these objects, and it is the same 124 grams regardless of their density. That added weight comes from the level of water going up. By submerging any of these objects, I'm lifting the water level by the same amount. Since the three objects have the same volume, each one lifts the same volume of water as I press it down, or allow part of its weight to submerge it in the case of the heavier objects. The force required to lift the water level is the same whether I pick it up in a cup or if I lift it by submerging an object in it. We should test that. We shall start with a full glass. I've colored the water with grape juice to make it easier to see. I believe the fluid is about 90% water and 10% grape juice, which itself is mostly water. The purple fluid you see is so close to the density of water, you'd need to have more accurate instruments than I've got to tell the difference. The full glass is sitting in a bowl because my wife doesn't know I'm using her stove like this. No forensic evidence will be left behind. This isn't just physics. This, I'm proud to say, is the perfect crime. I'll add enough grape juice to fill the glass. If you look closely, you can see a meniscus or surface warp slightly higher than the lip of the glass. It is completely full. In fact, there was a little bit of spillage from the last bit of grape juice added. Now I'll dunk one of our test objects. All of them exhibit different relative density to water, yet all three have the same buoyant force. Note that as I add weight to the object, pushing it below the surface, the water level rises, spilling over the top of the glass. The same thing happened a long time ago to Archimedes in his bathtub, and it was so exciting to him he ran naked through the streets shouting Eureka. I can understand his excitement, but I'll limit my enthusiasm in the name of academic integrity. The force applied down against the object lifts some of the water, just like a kid on one end of a seesaw lifts another kid on the other end. I push down, water rises, and it takes force to hold the water up against its weight. I supply that force by pushing down. In turn, the weight of the water pushing down into the glass and balancing the virtual seesaw is pushing up on the object. The buoyant force pushing up on a submerged object is from the weight of the water it lifted or displaced. This is the force of gravity redirected by hydraulics pushing up, just like a weight pushing down on one end of a seesaw lifts the other end up. We can verify that. Let's double check how much this object adds to water when fully submerged. This time I got 123 grams. And we will now abandon relative densities. We lost some volume of grape-colored water from our full glass by submerging an object. Pushing the object below the surface on a separate glass of water yielded a weight gain of 123 grams. So we'll measure out 123 grams of water without the relative density of any object playing any role. To my eye, it looks like enough water to overflow the glass. But no, it fits perfectly. If this principle is true, that a volume of water weighing the same as the indicated weight gain on the scales always equals the amount of water lifted by submerging an object, it should work with any object. We need something else to test. Fortunately, I have just the thing. This is an egg. It sinks in air. It sinks in water. And it sinks in olive oil. That will be of interest in a minute or two. Let's demonstrate that gravity drives buoyancy. Earth's surface gravity makes everything want to fall at an accelerating rate of 9.8 meters per second squared. Force is mass times acceleration, so with a constant acceleration from gravity, I can vary the force of gravity by varying mass. For those not comfortable with the G word, just think of weight. The egg has weight, the water down to every last individual molecule has weight, everything has weight. I'll use common table salt to increase the mass of the water. That will increase the force of gravity on the water. The force of gravity on the egg won't change because I'm not affecting the mass of the egg. I expect to observe the egg will rise. My presumed cause, as proponents of relative density like to state, is the force of gravity on the water. I increase the force of gravity acting on the water by adding mass in the form of salt. And the egg rises. But could it actually be relative density? Let's see if adding something the egg will sink in, something less dense than the egg, will also lift it in violation of relative density. I can think of two ways to do that. Our egg sank in olive oil. It floated in salt water. The egg in the medium of olive oil sinks, right? As the density of the medium goes up, things start to float. As the density of the medium goes down, things start to sink. Here's a review. The egg is on the bottom of a glass of fresh water. Add salt, it rises. Reduce the density of the medium by mixing in more fresh water, the egg sinks. The egg sinks in olive oil. Egg touching olive oil means sink in the relative density zoo. Here we have our egg floating in salt water. Off camera to the left, I've got a laser zip-tied to a tripod aimed so it's clipping across the top of the egg. Now I add olive oil. Note that the level of the salt water does not change because the olive oil is piling up on top of the water. But look at the laser. It now hits the egg quite a bit below the top. The egg has been lifted by olive oil, yet the egg will sink in olive oil. This is a relative density mystery because what would sink an egg resulted in lifting it. In fact, the egg had to also lift some of the olive oil by displacing it. There are two possible explanations. On a flat Earth, an egg's cries for help would resound infinitely over the plain due to some kind of acoustic perspective. Eggs would evolve to struggle up in olive oil so they could screech for mama. Some would say screeching for mama is consistent with flat Earth philosophy. But since rampaging chickens always come into view over the horizon beak first, I conclude the Earth is round. Acoustic perspective is a filmmaking term that has no bearing on this question. I remain unpecked by angry hens, so I conclude there is some other reason the egg rises. There is, of course, another reason, and the olive oil doesn't change the mechanism by which the egg floats. There is nothing new going on here at all. But like failing to see the curve of the Earth by crude observation, we didn't look closely enough at how the egg floated to begin with. We thought of the egg as floating in saline by displacing its own weight in salt water. That wasn't the whole story. The egg did not displace quite all of its weight in the water, but it was easy to assume it did. The whole volume of the egg matters. It displaced most of its weight in saline and a wee tiny bit of its weight in air. The weight of the saline it displaced, plus the weight of the air it displaced above the waterline, precisely equaled the weight of the egg. High-precision scales, the kind that cost as much as a Camaro, have to compensate for the buoyant force of air. Imagine the egg forced to the bottom of the container of saline and olive oil against its need to float. release the egg. It rises all the way up to the upper extent of the saline. If it encounters air, there is almost no additional buoyant force from rising further. It stabilizes with the saline supporting practically all of the egg's weight. If, however, it moves out of the saline up into olive oil, it still experiences a buoyant force. It's not enough force to lift the egg completely out of the saline, but it reduces how much of the egg's weight the saline has to support. Less weight to support, less displacement. The egg floats higher when it encounters a density boundary because of where its weight is being supported. But there is no force from relative density. Think about it. An egg sinks in olive oil because of density. An egg rises in olive oil because of density. Both cases are tied to a common thing, weight distribution from common forces produced by acceleration. The egg doesn't move from any force of relative density. It moves up or down from the force produced by gravity. I'll describe this phenomena with greater precision, complete with the simple math that describes it, in my next video, Floaters and Sinkers, Chicken Fried Logic. Hint, buoyancy disappears in 0G. The only way to calculate where the egg floats in 0G requires division by 0. Buoyancy doesn't work in 0G in the real world, and math doesn't allow a way to describe buoyancy in zero gravity. Funny how that works. Here's the full story. The buoyant upward force exerted on any submerged object is an emergent force. It appears because of weight. That weight can be force from centrifugal acceleration, quaint Newtonian concepts of mass attracting mass, or an observed result from Einstein's curved spacetime. Eggs won't float unless gravity is present to cause buoyant forces to emerge. Curiously, it's not the weight of the egg that matters. In fact, the weight of the egg has nothing to do with the buoyant force. The weight that matters is the weight of the medium, but only the part of the medium that's displaced. The weight of a volume of water equal to the volume of a submerged object, no matter the object's weight or density, sets the buoyant force. If the buoyant force on an object is greater than the force of gravity, the object floats. If gravity is greater than the buoyant force, the object sinks. Objects of equal volume, when submerged and held in a position not touching the sides or bottom of a container of water, add weight to the glass regardless of the object's weight or density. The volume of water lifted up or displaced by the object weighs exactly the same as that acquired weight from submerging the object. You could say that's a long-winded way of saying objects less dense than the medium they're in float and objects more dense sink. But that would ignore the inconvenient fact that when an object is submerged, it lifts part of the fluid it's in. The buoyant force appears because the lifted, displaced fluid has greater potential energy because it's been lifted against its weight. Like everything else in this universe, the medium is always seeking lower energy states. The force of gravity is proportional to an object's mass. The force of buoyancy is proportional to an object's volume. The force of buoyancy is therefore set by the force of gravity acting on a portion of the medium equal in volume to the object, but independent of the object's mass or weight. There's one last thing I should share. I said there were two ways I could show a less dense medium lifts something it would be expected to sink, didn't I? Let me pay that debt now. Here's a mug of salt water, briny enough to float our egg. I've cut the bottom off a water bottle to separate fluids. It's not a container anymore. It's a funny-shaped tube open at each end. Let's add a little grape juice to make the water easier to see. The egg goes in the tube and into the saline where it floats as expected. Note that water seeks its own level and is at an equal height inside and outside of the tube. Yeah, don't expect that to last. Now my somewhat chubby lab assistant will pour olive oil on top of the saline outside of the tube. No olive oil goes inside the tube. Note that by adding olive oil, the dense water inside the tube is lifted by the less dense olive oil. The egg, floating on top of the salt water inside the tube, is also lifted by the less dense olive oil. By the way, do you see the equal sign here? You remember the two kids balanced on the playground seesaw? That was an equal sign writ on the natural world. The same thing happened here. As the weight of the olive oil was added outside the tube, like adding weight to one end of a seesaw, the saline level outside the tube went down. The portion of fluid below that lowest saline level acted like the fulcrum of the playground seesaw. The saline inside the tube lifted up, just like the other end of the seesaw. And let's look at fluids always seeking their own level. Here, the fluid level outside the tube is above the level inside the tube. There's an inch difference. Natural laws worked out by Pascal indicate that connected chambers always seek their own level. And they do, if you look at a complete explanation of the principles involved. As we see here, fluids can play tricks. They don't always seek the same physical height. They seek the same potential energy in the gravity field. The less dense olive oil experienced a lesser force of gravity than the more dense saline. It has to be higher to be at the same potential energy state as the saline inside the tube. They are both under the same acceleration of gravity, which is constant. They are not experiencing the same force of gravity. Force varies with mass. The acceleration is constant. This stair-step in the fluid level forms for the same reason water conforms to a spherical shape when acted on by center-seeking gravity. The free surface of a fluid will conform to the shape offered by forces acting on it, such as gravity. Those are my conclusions, reinforced by people I respect. More than anyone's opinion, no matter how much I appreciate my betters, these observations are reinforced by the predictable, calculatable, perfectly math-consistent cosmos we live in. None of these scenarios are offered in the context of scientific experiments because I don't want to argue about what an experiment is. These are observations. If you doubt them, test them. I'll be fascinated to hear your conclusions. I have a correction, though. This is not an egg. Thank you for listening. If you would like to have more food for thought, I've got some other interesting effects to showcase. Whether or not you want to see any more, I appreciate your dropping by. Please click the subscribe icon today so you can avoid the rush later. Y'all have a nice day.